class. Welcome to our third class. Today we are going to be talking about probabilities and data. We're going to be discussing several concepts regarding how is it that we can model and understand data based on probabilities. You know that data is not general, it's not binary, so things tend to have, or events tend to have associated different probabilities, and that's what we're going to be looking into today. How is it that we can model the probability of a given event happening, and how is it that we can measure different probabilistic events. So we'll also be talking about expectation and entropy of distributions, and we'll talk about continuous and discrete distributions and about different types of joint or conditional distributions, so different ways in which we can model data. We'll also be looking into how we can do those things in R. Okay, so it's going to be on one hand the theory of the models, and on the other hand, how these things can be done in R. It's going to be a very wide array of different concepts with apparent no relationship to each other. So bear with me. All these are important concepts that you'll need to know about, and it's going to give us a foundation for future classes. As I was saying before, nature is not binary. Okay, things do not either happen or not happen, but events in life might happen with a given probability. And in fact, given any type of experiment, we are typically going to have a set of different possible outcomes. Okay, so what probabilities do is that they basically allow us to measure the likeliness of one or the other event happening among all the different possibilities. So today, we are going to see, as I was saying, the foundation for many of the classes that we'll see in the future. So some of the techniques that we will be seeing in future classes are going to be based on probabilistic concepts that we'll see today. So again, it's going to be, concepts here and there without any type of relationship, but that will be really useful for future classes. And what we are going to do in this class is just, learn basics about different types of probability distributions and how we can handle them in R. When we talk about probabilistic experiments and variables, there are different types of classifications that we'll be looking into. First thing we're going to be looking into is whether the variables that we're talking about are deterministic or random. Okay? If we know the outcome before the experiment happens, that's when we can say that the variables are deterministic. So for example, 2 plus 3, we always know that it's going to be 5. And we also know that 2 parts to hydrogen and 1 part of oxygen makes water, and it's always going to make water. Those are deterministic variables. However, things like, for example, tossing a coin. When we toss a coin, we know that it's going to be that there are 2 possible events happening that might happen. Okay, but we don't know which one is going to happen. If the coin is fair, we know that the 2 events are equally probable, but we don't know which one is going to happen. Same thing for rolling a die. Numbers between 1 and 6 might be the outcome, but we don't know which one is going to be. Although we know that if the die is fair, all the events from 1 to 6 are going to have the same probability. All the set of possible outcomes that a given event has. So for example, when we roll a die, we know that we're going to get numbers from 1 to 6. Or when we toss a coin, we know that it's going to be either head or tail. This set of values is what we call the sample space. So as I was saying, today we're going to see different concepts, probabilistic concepts, but we're also going to learn how can we model these concepts in R. Okay, so the first important thing when we work with probabilistic distributions is how do we define a sample space. So the way you can define a sample space in R is basically creating a data frame. Remember that we learned about data frames in our previous class. So you need to create a data frame where in this case, for example, the event is drop a cup on the floor and the cup might fall down or up or on the side. Okay, so we're going to declare 3 different potential outcomes. So the sample space is going to have 3 different potential outcomes. Okay, so what we can do is go to R. We can basically define a data frame. That's going to define the event lands, and it can land down, it can land up, or it can land on the side. Okay, so if you're an S, basically we have here our sample space, which is going to have down, up, or side, the three potential outcomes. Similarly, another thing that we can have in R is basically, as we mentioned in the previous class, R has a lot of data sets and a lot of functions already defined and packaged in libraries. So you basically need to declare that you're going to be using a given library or a function from a given library before you can use it. In fact, R offers a large set of different probabilistic functions and probabilistic experiments. So there's already an experiment defined in R that allows you to toss a coin, okay? And it's going to give you the probabilities or the different sample space, the different types of events that different probabilistic experiments can have as outcomes. So for example, the library that we're going to be using now, it's called prob. So let's load that library, okay? Wait until it's loaded, and then there's an experiment in this library called toss coin. Okay, so you can in fact decide to toss one coin, and what the output of this function is basically going to give you the two potential outcomes of the event of tossing a coin. Okay, so you don't need to actually, the example that we gave before about throwing a cup is something that it's not one of the well-known probabilistic experiments, but tossing a coin, rolling a dice are typical experiments in probabilistic distributions. So those are experiments that are already defined in R. Okay, so you don't need to define or to create a data frame to define all the potential different events, but rather, make sure that you use one of the existing experiments in R, in the library called prob. And this is another example. So you can toss one coin, but you can also toss, for example, 3 coins. And all the outcomes are here. So basically, if you toss 3 coins, there are 8 different potential events that can happen. The first event is that you get 3 heads. Second event is that you get 2 heads, and so on. So it's basically what the toss coin creates is all the different types of events that might happen, given that you are tossing 3 coins, and given that the 3 coins are fair, meaning that all 3 coins have the same probability of getting heads or tails. Okay, another experiment that we can do, typical probabilistic experiment, is rolling a die. So you can also write roll die, 1. So this is basically going to roll 1 die, and the potential outcomes that we can get are numbers from 1 to 6. You can in fact roll also 2 dice, and we have 36 different events. Okay, because you have 2 dice that are going to get independent events from 1 to 6 each other. Another typical probabilistic experiment is working with urns. Okay, so typical experiment, imagine that you have one urn that has X balls with different colors. You shake it, you grab one, you take a look and see what's going on. Okay, typically when we define those experiments, we want to see what's the probability of drawing or extracting from the urn a ball that is red, or extracting from the urn a ball that is blue followed by a ball that is red, the typical probabilistic scenarios. So it turns out that there's also another function that we can use in R to work with urns, and basically it's called urn samples. Urn samples, the first parameter is the number of balls or elements that you're going to have in the urn. Then the size is the number of samplings that you want to do. And then you have to declare whether the samplings are with replacement or not, meaning whether you put the element back into the urn or not, and then whether the order matters. Okay? And then basically once you launch that event, what you're going to get as outcome is the set of possible outcomes from the experiment. So let's see a couple of examples. This is an exercise that I'm posting, so before you turn into the next slide, you can stop the video and try to think about how would you define those. Okay? Taking into account that this is the function that we are using, how would you actually create an experiment with the urn samples function that allows you to understand how many different events we observe when the extraction order matters? So we have an urn with 3 different balls. We draw 2 balls without replacement, so we don't put it back into the urn. How many different events do we observe when the order matters? Okay, so it's not the same getting first ball 1 and then ball 2 than getting first ball 2 and then ball 1. And how many events do we have when the order is not relevant? So getting out ball number 2 and 1 is the same as getting out ball number 1 followed by number 2. and what happens when we replace, when we put the ball back into the urn. So all these things, we can do them automatically. You can reason them without, the need of using R, but you can also do them automatically. How would we do it without replacement? So without replacement, you would basically use, again, the urn sample. So we use the command urn samples. We're going to define, we have basically 3 different elements in the urn, 3 different balls, for example. The size of the experiment is going to be 2, so we take out 2 balls from the urn. We don't allow for replacements, meaning every time we take out 1 ball from the urn, we don't return it into the urn. And basically the order matters. Okay. So we have 6 different events. What this means is that, you can extract first ball number 1 and then ball number 2. You can extract first ball number 2 and then ball number 1. Same thing for 1 and 3, and same thing for 2 and 3. Okay? And 1 and 2 is different from 2 and 1 because order matters. And the reason why, we don't have more events is basically because we don't allow for replacement, so we don't put the ball back. Okay, so we get 6 different events. If, say, for example, the order doesn't matter, then we are losing half of the events because 1 and 2 is the same to 2 and 1, 1 and 3 is the same event as 3, 1, and 2 and 3 is the same event as 3, 2. So in this case, we would only have 3 different events. Okay? And what happens if we actually put back the ball into the urn? So we have a replacement that is true. Sorry. So we would have replacement equals true. Let's put here true. And here we would have 6 different events. Okay? And then if the order matters, we would basically have 9 different events. Okay? We replace. So meaning if we can replace, we can get 2 times the same ball. So we have the event 1, 1, the event 2, 2, and the event 3, 3 that we add up to the previous events. Okay? Because if it's ordered. And if it's not ordered, okay, remember that we had just 3 events, so here we are adding 3 more. Because we allow for replacement, we are adding 1, 1, 2, 2, and 3, 3. Okay?